Recall the argument I made in Class 12 that we can treat the error term of a regression empirical model as if it were generated by a random process. I'm going to appeal to the central limit theorem to argue that the error of the ith observation is normally distributed with some variance sigma squared sub I. Stop a moment to jot down why we can be confident that the expected value of epsilon I is 0. The exact form of a random generating process and its probability distribution is determined by underlying parameters. For the normal probability distribution, these are the mean and variance. For the random generating process that yields the linear regression model, these are the mean and variance of epsilon sub I and the coefficients of the regression equation. In the first part of the course, we discussed statistics as summary measures for describing data. If the data they are describing are realizations of some random generating process, as we presume for the regression model, then those statistics are also estimators, that is, functions of one or more random variable that yields an estimate of a parameter characterizing the probability distributions for the random variables. When I estimate the bivariate regression for n observations, y hat, a, and b are all estimators because they are functions of random variables. This is easy to see in the context of the ordinary least squares regression technique. We derived this expression for the slope coefficient, in which b is a function of y, as well as deviations for x from its sample mean. But y is in turn a function of the n random variables epsilon sub I. A is a function of b, and y hat is a function of a and b. The reason we use the ordinary least squares regression technique to calculate the coefficients is because its estimators have a number of desirable properties that we will study at greater length in your next econometrics course. In particular, if a set of assumptions called the classical regression model hold, then the regression coefficient is unbiased. That is, the expected value of b is equal to the true beta. And it's efficient in the sense of having the minimum variance of any other linear estimator of beta. Perhaps even more important to us as econometricians, under the assumptions of the classical regression model, we can derive the variance of the regression coefficients as a function of the data and the parameters of the empirical model. And that is the critical step in deriving the probability distribution of the estimated coefficients. Textbooks vary in the lists they give for the classical regression model assumption. Here's my list, and I'll include it in the handout during Wednesday's class. Under these assumptions, we can appeal to the central limit theorem to derive the probability distribution for the bivariate regression, slope, and constant shift coefficients, and extend this result to multiple regression equations. If you tell me beta and beta naught, sigma squared of A and sigma squared of B, I can obtain probabilities for any events involving A or B. That is, the probabilities that A or B will take on any range of values. For example, suppose beta is equal to 4 and sigma squared B is equal to 9, and we want to know the probability that B is less than 7. This is equivalent to finding the probability that a standard normal random variable is less than 7 minus its mean divided by its standard deviation. That's equal to 1. Then we want to find that probability in the table, so I draw the picture and find in the table the probability of being less than 1, which is 0.841. Thus, treating the regression coefficient as an estimator of the underlying parameter allows us to make probabilistic statements about how close that regression coefficient is to the true coefficient.